Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. The usual reminder that if you do enjoy the show, please consider supporting us through Buy Me a Coffee. It really helps us to keep making the show and for us to keep the lights on. So yeah, please do consider supporting us there through that. You can find links to that in the show notes and on our socials if you do fancy buying us a coffee. One more announcement. We also have a listener survey out at the moment. So if you do feel like giving us some feedback and helping shape the future of the podcast, please do consider filling that out. You can also find that on our socials, and I'll drop a link to that in the show notes as well. So please do give some feedback. All feedback welcome, and please be candid with it. So yeah, please check that out. Cool. On to today's podcast. And it gives me great pleasure to say I'm joined today by Yifei Yang from the University of Wisconsin-Madison, who will be taking us on a journey through query processing. We're going to be talking about his 2024 cider paper, Predicate Transfer, Efficient Pre-Filtering on Multi-Join Queries. Yifei, welcome to the show.
Hi, thank you for introduction. Hi, nice to meet you, Jack. Yeah,
Likewise.
glad to be here.
I'm really excited about this conversation today. I love query processing, so I'm really excited to learn about some more about it today. So before we do dig into and talk about query processing and all of the things and predicate transfer, tell us a little bit more about yourself and how you kind of ended up in research and specifically how you kind of became interested in data management and the query processing side of things.
Okay, sure. So I'm currently a third-year PhD student at University of Wisconsin-Madison, and my current interest of the research is generally broad query optimization on OLAP. In other words, analytical query processing for relational databases. So before I'm being this stage, I contact databases when I was an undergraduate. So actually, at that time, I don't know what research I should do. I just know I want to do some research. And I just broadly contact professors. And finally, it just luckily got adopted by a professor who took interest in graph databases. So at that time, I don't know any details about relational databases, but just had a very brief research period on the graph databases. But then I realized, wow, if I can make everything faster, just like you do a running competition, well, you will get excited when you make your query processing faster and faster. And then I kind of shaped my interest in make something faster, no matter whether it's graph query processing or relational data processing or some others like general distributed system or there are some analytical tasks on that. So when I step into the master program, I also find so I will shrink my target to some latency aware optimization fields. So I got a chance to work with the professor on Polystore, which is execution on multiple databases in multiple models, like relational, like graph, like XML and documentation, something like that. Because I have some little background on graph processing, so this is maybe the reason he wanted to accept me. And during this time, I also contact for preparation of my application PhD. So at this time on the summer, I got contact with my current advisor, which is interested in researching on traditional analytical query processing. And then I got onboarded. That's the basic story. It's a long story, right?
No, that's nice. Yeah, I mean, just kind of going back to something you said at the very start of the answer, that you kind of knew that you were attracted to research, sort of, even from an undergraduate sort of level. What was it about research that was sort of so appealing to you?
Yeah, actually, the reason at first is something very trivial. I just feel if I start working when I finish undergraduate or master, I just don't know things enough, don't know things deeply enough. For example, I don't know what team I should work on. I don't know what technology, what kind of area I fit most. So I want to discover what I like. And during the process, I find database is something really interesting. So actually, another reason that I don't want to work at that time. Okay, so something combined to lead this result. I want to apply for a PhD program.
Yeah, I can totally relate to that as well. Yeah, it's kind of similar sort of thing from my sort of education as well. I was kind of like, "Oh, I'm not ready to go into industry or anything. Yeah, I want to keep seeing how things go. But yeah, also as well, something that you said about elsewhere and about sort of making things faster, like running faster, making things faster. It gives you a nice kind of that dopamine hit, right? It gives you a nice sort of thrill when you kind of making stuff faster. So yeah, can
Yeah.
definitely can definitely get on board with that as well. So let's talk about how you've made query processing faster anyway. So, but before we do that, I guess we
Mhm.
need to set a little bit of background context for the listener. So, I mean, kind of build it from the ground up here for us. Kind of what are joins? And these are really important in query processing. So, yeah, kind of what is a join? And then what are all the family of joins that go with it? It's like multi joins. And yeah, I guess also kind of it's in the title of the paper that we're going to be talking
Yeah.
about. Yeah, what's pre-filtering as well? So, yeah, give us some background, set the scene for us.
Yeah, sure. So when you store data in the databases in a regional format, basically you just have tables. And you don't want to store all the data in a very giant large table because you will get many rows, many columns. People will usually decompose all the information into many pieces of tables. For example, you can have a table storing your person's information and another table storing your scores for each person and some other table stored for example, the contact information and whatever. But those information are split so that each table is responsible for one particular category. And when you want to query, you probably need some information not just from a single table. So you need to, for example, you want to find the score of a person given a name or a phone number. You need to somehow combine information from multiple tables to get the rows or information what you want. So in this case, you need to basically connect this information to tables, what we call a join. So that's the high level definition. So in the grammar level case, basically the join requires you to specify two tables at least, and you can specify some predicate on that. So if you do not specify any predicate, you will have a Cartesian product where each of the maybe one row will be connected with every other row in another table. People usually do not do that because it does not make any sense in most cases. People need some predicate to specify what kind of information they want. So basically, maybe in one table, you store a person ID. In another table, you also have a person ID referencing to the personality of the first table. Then when you want to combine information, you basically check for each row in that table whether there is a row in another table has the same person ID. Then you can match, well, the information of these two rows point to the same person. And you can do some further processing on that. This is called a natural join. Yeah, and basically our research is on top of this natural join. There can be many more complex join like outer join, semi join, but it's basically extension of this. So this natural join specifies the computation between one pair of tables, basically two tables. And sometimes you need information from more than two tables. For example, you need three tables. What you do is basically you join this first and the second tables first. You get maybe intermediate table, and then you join the intermediate table with the third table. You will get two joins, and this is what we call multi-join.
Okay, nice, cool. Yeah, I mean, I can definitely see the need for filtering because if we've got two pretty sizable tables and we do the Cartesian, we end up with a Cartesian product that could be a huge table, right? So yeah, and also just to kind of recap on the multi join there, it's the scenario where we want to join information from multiple tables and we would join two and then we get an intermediate table and we join that table with the third table and I guess the process could go on for n number of tables depending on
Yes.
how many tables were part of your query or what computation you wanted to do. Cool. So with that sort of scene set then, so can you kind of tell us where predicate transfer fits into this story then and give us sort of the elevator pitch of your work?
Yeah. So when you observe some benchmark queries, for example, TPC-H or some customer queries, maybe you can just focus on a single join. I'd say both of the table is 1 million rows, for example. And you can observe that maybe in the result, you only get a 100 row, which is very small because you have a very selective predicate uh, applied on each of the table. So what we observed that is most of the rows in the base table, which is the joining table, will not contribute into the final result. So for example, many rows of the first table after filtering do not have a match on the other table also after the filter applied. So in this case, if you simply join this table first, you probably will get a very large intermediate result. And it's only filtered when you have more and more tables joined. And only finally, those unnecessary rows will be filtered out. So what we hope is to filter these rows out, maybe not entirely, but almost maybe 90% before any join occurs, because join is very complex. If you join many rows, you will have a large overhead. But if you join with multiple inputs with pre-filtering applied, you will get a very cheap computation.
Okay, nice, cool. So if I'm understanding this correctly, there
Mm-hmm.
is a scenario in which, well, even when you do some filtering, that
Mm-hmm.
it sometimes isn't actually that what's the word to say? So you do the filtering and you still kind of then you do your joint and you still end up with a lot of like not many matches, even though you've done your filter. So the filter kind of hasn't really had that much of an effect. Is that sort of part of the
Yes.
problem there? Okay,
Yes.
cool. So yeah, I'm getting it now. The way I can see where the predicate transfer is going to fit in here. It's like, okay, we're going to try and improve this situation and make sure that kind of we're a bit more effective with this. Okay, cool.
Yeah.
So I know that from your paper, bloom joins, another type of join, is important in your work here. So tell us about what bloom joins are and how they work, and that can, I guess, lead us into how the predicate transfer algorithm works.
Okay. Yeah. So this depends on the join algorithm of maybe the natural join, for example. There are several algorithms. The most popular two are just a hash join and a merge join. So, and among these, hash join is also most popular. So hash join, basically you want to build your hash table on your smaller side of the joining tables. And then you probe the rows of the larger table one by one into the hash table to check whether there's a match. If there's a match, we emit one outer row. So Bloom filter is used to optimize this hash join. Since hash table, the right to the hash table and access or probing to the hash table is a little bit expensive. So people invent Bloom filter, which is a very lightweight structure. Its size is much smaller than the hash table, and its write and access is also much faster. So basically, the shape is the same. So you build your Bloom filter on the smaller side, just the same side of the hash table building, and then you also probe each row of the larger another side of the table into your very small Bloom filter. And this technique will not guarantee you will figure out all the matches, but it will filter out most of the rows that will not have a match. So it will have no false negative, but have some slightly small false positive rate. But it's good enough because its execution is so fast. So we do not care whether it's filtered out entirely or not. Because after this step, we will also run regular hash join, no matter what.
Okay, cool. Yes, so I can see why the no false negatives is really important there, because you don't want to discount anything
Yeah.
that actually is a match, and we can allow for a small number of false positives. I always get my false positives and false negatives the wrong way around, so forgive me if I've said that the wrong way around. But yeah, and then so you can have a few, because then we can kind of, I guess, clean these up a little bit afterwards. Okay, cool. So tell us about the predicate transfer algorithm in a little bit more depth, then, because I know there's two phases to it. So walk us through it from the kind of, I don't know, maybe give us an example that can be useful to walk us through it. I know the floor is yours to explain this, Yifei.
Yeah, sure. So what we started from a very traditional academic algorithm called Yannakakis algorithm. So this one invented maybe 20 or 30 years ago, which is used in acyclic queries. Actually, this people may not be familiar with whether the query is cyclic or cyclic. So the acyclicity means there's no triangle or a loop when you're joining tables. So that will be just a tree structure based tree, the join graph. So this algorithm, the detail a little bit complex, but basically when you run this algorithm, it will do a bunch of semi join in the join tree from the leaf node to the root. and then from the root to the leaf in a two passes way. All permutation are semi-joint. And after this kind of magic processing, it guarantees that if there is a row remained, it will contribute to the final join result. So which
Okay,
means
cool. Yeah.
it filters other rows which are not unnecessary.
Yeah,
The
can I just
detailed
ask you
proof a
really
little
quick?
bit are complex. Yeah.
Sorry, if just to jump in real quick. What's a semi joint?
Oh, sorry.
That's
Semi-join is
okay.
something like, yeah, you join two tables, but you only want to keep columns of one side of the table. So for example, you have two tables, maybe the columns are A, B in the first table and C, D in the second table. After the joining in the natural join, you only want to keep A, B. So it's similar to an exist clause where if for the first table, if there is a row that has a match in the second table, we keep that row. We only keep row of that table. And anything in the second table, we don't care about that. So we just try to check whether there's a match from the specific row in the first table to the second table. That's a
Okay.
semi-join. Yeah.
Okay, cool. So I interrupted you there. Continue with your explanation. Sorry.
No, it's okay. Yeah, sorry, I forgot to bring out this basic definition. Yeah. So basically, do this kind of semi-join in two passes in a magic way. People can figure out and they can prove that as long as there is a role that contribute to the result, it will be preserved. If it's not going to contribute, it will be discarded. Yeah, that's a very old traditional algorithm. And as we mentioned, join is very expensive. There's no exception for semi-join. It's also expensive. Yeah. So basically, you can think our idea is to apply this lightweight Bloom filter to replace semi-join, so that we can still filter most of the rows, but we don't need the guarantee. We don't need to guarantee 100% filter out. We still filter out most of the unnecessary rows, but we are efficient in this filtering phase. And after that, we do regular join. The regular join will start from a very small base table inputs, maybe a little bit larger than the reduced table of the Yannakakis algorithm, but will not be a large difference. The join phase will be always very efficient.
Nice, cool. So yeah, I mean, I guess we could maybe dig into the actual I guess the steps a little bit more. I know because in your paper you give an example with one of the queries from TPC-H.
Yeah.
So maybe we could talk through how the algorithm would work on that example maybe.
Yeah, maybe, yeah, I think we have a better favorite part. We always use that in
Okay.
experiment and discussion,
Yeah.
which is Q3 actually. So Q3
Okay.
basically involves only three tables.
Right.
Smallest can customer, a middle one called orders, and largest called line item, right? So basically it's a chain structured join. You join customer with orders first and then with line item. So it's definitely acyclic. So Yannakakis algorithm must work on that. So the tree structure is also simple. It's just like a chain. So what we do is let's pick maybe the starting point as a customer table, maybe the leaf as customer table, and the top or the root as a line item. We go from customer to orders and line item in the forward direction during the transfer. So what this I will introduce the details of the forward transfer next. So basically, you start from the smallest table customer, you build a Bloom filter on the join key between customer and orders. And then this Bloom filter is used to filter the rows on the orders table. And orders will be get reduced, maybe to 10%, for example. And we use the reduce table, 10x smaller orders table, to build another Bloom filter on the join key between orders and line item. And this Bloom filter is used to filter line item table, maybe reduced another 10x on line item. Yeah, and this forward path. And when we do the backward path, the reverse direction, do the similar thing, which is we start from the reduced line item table in the forward path, basically, for example, 10x smaller of the original size. We build a Bloom filter using on the join key between line item and orders. And this Bloom filter is used to filter already reduced orders table. Maybe you get another 2x smaller, right? Then you start from the 20x smaller orders table. you build another Bloom filter on the join key between customer and orders. And this Bloom filter is used to filter the customer table, which may shrink maybe by 5x on the customer table. And basically that's all done for the other tables to reduce the size. And after that, you can do regular join from the very smaller tables.
Perfect. So we've made our problem massively smaller by doing these two passes. That's awesome.
Yeah.
Can you tell us a little bit more about the implementation here then? So like, how easy was this to implement in practice? Now, what did you implement it in? And how easy was it to do, I guess?
Yeah, so if you had this idea on your mind, probably it's not hard, but when you go into the real code, it will be a little bit tricky. So we have a code base called flex push down DB. This is just a I know the code. Maybe it's a little bit easier for me to do. So basically, this code base is similar as maybe open source ones like DuckDB, like Presto, like SQLite, Postgres, some OLAP databases. So it has joins, it has Bloom filters. So basically, we start from the original execution where you already get a query plan, right? We add a phase before this execution phase called pre-filtering phase. And in the pre-filtering phase, we scan the base table one by one, and we construct those Bloom filters, apply those Bloom filters in the same direction that as the example that we just went through, right? From customer, orders, an item, and go back. And then we will store our reduced table somewhere in memory, just as intermediate result, and use this intermediate result tables as the new input of the execution phase. So the execution phase do not need to scan the original table. They will just scan those reduced table produced by our pre-filtering phase. And then both phases are connected and will go smoothly.
Nice. Yes, it's obviously you knew the code. So how long was the implementation effort though? Because you said as soon as you it's a simple idea, but as soon as you go and actually try and put this down in code, it can be quite challenging, right? It's never as straightforward as you think, and there's always bugs and whatnot. So yeah, was it a long implementation effort? Like, what was that like?
It's not too long. Basically, you have to have some preparation. For example, you have to implement your Bloom filter first. That's something
Right. Okay. Sure. Yeah.
right? Yeah. When you have this kind of tricks, you won't get a very long code. You just need to order those tables and specify which table starts with the Bloom filter build first, and then what is the next table to use that. And after this, use what is the next table to build a second Bloom filter. You just need to specify those orders. In our paper, the order is always the page transfer is always occurred from the smaller table to the larger table. So in our Q3, it's customer orders line item because this is sorted based on the sizes, right?
Sure.
So basically, in the implementation, you don't need to specify the order. You can have your own customized order. This does not matter, but you just need to specify the order, and then everything will go smoothly as because you just call the libraries of the build Bloom filter on some columns. You call a library of the problem filter using some table on some column, and keep doing this.
I like it. Great. So let's talk about some results then. So, well, first of all, maybe how did you go about evaluating predicate transfer then? So what was your experimental setup like? What did you compare it against? Yeah, what was that evaluation like?
Yeah, so basically start from the very famous TPC-H benchmark. And at that time when we submit the paper, the prototype is not matured enough, which is our transfer technique only applies on single thread execution. So we haven't finished parallel and something like distributed execution. So we only measure a very smart data set, which is which is factor 1, which is 1 gigabyte, and 10 gigabyte data set using a single thread. So in that case, we only also compare with ourselves. We didn't compare with some other existing open source or commercial systems. Since that would be too much work, right?
Yeah.
we want to get the paper done as quick as possible. So we
Yeah.
already figured out we got a very large gain. And I think we just think that's good enough. Maybe we should try to submit first. Yeah.
Okay,
That's
cool.
story to evaluate.
That's our evaluation, mate. Awesome stuff. So
Yeah.
yeah, I guess let's talk some numbers then. So kind of what was the performance number? What was the performance like?
Yeah. So the performance really depends on how many tables you have in the joint, right? So if you have many joints, the transfer will make a very large impact because a single predicate can be transferred to everywhere in the joint table. But if you have just a two-table joint, it will behave similar like a traditional Bloom joint because you don't have the possibility to transfer further. So we observed that on average, the average means geomean. We use geomean to measure. The speed up can be 3x to 3.5x. But on some very large queries like Q2, Q5, or Q21, it can be more than 10x to 60x on a single set execution because sometimes they have 8 tables in the joint graph, or they even have a cycle.
Okay.
A cycle is something really interesting because Yannakakis, the traditional algorithm of Yannakakis cannot guarantee the optimal. But we also do not need to require this optimality. We just want to filter as much as we can. So actually, in a sticky case, which is Q5, we do a very good job compared to Yannakakis. We even filter more rows than the traditional algorithm does because there's no guarantee, but we can filter a lot more edges than Yannakakis do. So we follow every edges in the graph, but Yannakakis have to break the graph, a sticky graph, into a tree somehow. So we have more opportunities. So yeah, so the high speed up queries can get again up to 60x, but some small queries can just have a speed up between 1 to 2x.
Oh, cool. Yeah, so it's kind of it's very much related to the sort of the size of the tables, the number of the tables, and then the kind of whether they're cyclic, acyclic, or not.
Yeah.
Kind of a few things have been bouncing around in my mind as we've been chatting about this, and the order in which you choose to actually do this join is you saying at the moment it's a manual process where you're like, okay, we're going to use a simple heuristic in the sense of we'll use the smallest first or the biggest first or kind of or whatever. Is that decision at the moment kind of is the humans inputting that decision, or is the scenarios in which other types of orders might be better depending on the type of the query?
I see. It's basically following the traditional wisdom, which is you usually want to build your hash table on a small table and probe in a larger one. So basically adopt the same strategy. We want to build Bloom filter on a smaller one and probe on a larger one. Okay. Following on this trick, we just order the table by the sizes and from the smallest to largest. Yeah.
Gotcha.
And actually we have some experiment to show that maybe it's not much difference when you start from the smallest or the largest.
Oh, really?
Anyway, you have anyway you have to scan the table once when you build or probe the Bloom filter. And build and probe and Bloom filter, the difference is almost similar. But in hash table, it's different because when you build a hash table, it's more expensive than probing a hash table.
Yeah, awesome stuff. Yeah, so that's fascinating. So also as well, kind of this principle of using of Bloom filters, can it be applied to other joins, well, I don't know, like worst case optimal joins or things like this? Well, could you apply the same sort of principle to that as well, to those types of algorithms, and use it as like a generic pre-filtering sort of step?
Yeah, that's a fantastic question. Actually, we got this question many times, including the conference, including some offline discussions. Yeah. I think worst case optimal join can be the future actually. Yeah, but I'm not sure whether it will get as successful as today's binary join because it's very well optimized. So to combine predicate transfer with worst case optimal join, I feel a very naive approach is just like separate the two phases. You still do the transfer with the table size first, and then from the new table, smaller table, you do the worst case optimal join. But I think there can be some opportunities to couple these two techniques more tightly instead of isolating in two steps. And we probably want to dig further onto that. But currently, we don't have a very concrete answer.
Definitely one for an interesting one for future research. And also, I just kind of introduced worst case optimal joins there without describing it. So maybe you could actually give us you'll be able to give a better description of what worst case optimal joins are than I. So can you maybe fill the listener in on that as well? Yeah.
I'm not an expert on that. We have a student working with together. Actually, I know the idea from him. So I can only tell some high level things that I understand. So Basically, in a binary join, you have to join two tables to produce some intermediate result first and use this result to join another table, which is the third one. But in the worst case, probably you want to produce the row as a whole when this row goes over all the tables for the probing or check whether they're the match. So when you only produce a row, when you guarantee that this row will be in the final result. So for example, there are three tables. I think if you start from the first table, you will check whether they're the match on the second table. And if they're the match, you keep checking where they're the match on the third table. Only when all the conditions are met, you will emit that row. There probably will be no intermediate result. And on the complexity, it has a very good, a strong property on the cyclic queries. For example, in the triangle queries, it shows the complexity is smaller than binary join. So this complexity will be n to the power of 1.5. Let's assume every table has n rows. But in the traditional binary join, it's n square, something like that. For the proof, I don't understand, but I just remember this property.
There's a better description of it than I could give. So no, that's awesome. Cool. Right. Yeah. Also, with predicate transfer, it kind of feels to me pretty much like a win-win in most scenarios. But are there any sort of cases or situations in which you think that the performance of it might be sort of suboptimal, essentially, or like any sort of place where it's like, yeah, it's probably not going to give you that much of a win? Yeah.
Yeah, definitely there should be. So package transfer is just used to pre-filter those unnecessary rows. So a very simple contract example is that you don't have unnecessary rows. You know that most of the rows will join the final result, even though the result may be too large, but you don't care. In this query, there's not too many unnecessary rows. In this case, package transfer may incur an extra overhead, but filters out a very few number of rows. Yeah. So the thing is, in our code base, maybe our code is not fully optimized. We observe that Bloom filter is always too fast that even though you do this extra work, it won't incur too much overhead. But we also observe that in some commercial system like DuckDB, Bloom filter is not a negligible overhead compared to Hashtun. And in this case, the suboptimal case will be more obvious, I think, and we should optimize on something like that.
Yeah, because I was going to say, as we've kind of been talking about as well, kind of the cost of creating the Bloom filter each time is obviously it's non-negligible, right? There is some cost there, so I guess there is scenarios in which that. I mean, it maybe is very much implementation dependent as well. You can probably have a really efficient implementation of it as well, high performance implementation. But yeah, that's interesting to know as well. Cool. Yeah, I guess so. I kind of guess with that then, where do you said this earlier on in the chat that this was a sort of very sort of initial stage sort of project, kind of putting the paper together. It was kind of done on kind of quite a quick time scale. So where do you go next with it? What's the sort of next on the research agenda for this project? I mean, it seems like there's a lot of opportunities there. So yeah,
we got the same feeling actually. Yeah, we thought there are many new problems worth digging further. So for me, because when you submit the paper, it's just a single thread execution, right? So a natural extension is just to support the parallelism and distributed execution, which is currently I'm working on. Yeah, I need to deal with some bugs, performance bottlenecks before getting everything done. Yeah, and some other students are working on, as you just said, how to do this transfer adaptively to avoid some unnecessary overhead. Yeah, and some others are working on whether the packet transfer will affect traditional join ordering. Some interesting things. And some others are also brainstorming with packet transfer combined with worst case optimal join. So there are many interesting ideas.
Yeah, that's sure. It's going to spawn I'm sure quite a nice amount of research. Is this paper? So no, that's fantastic. Look forward to seeing the fruits of it as it develops over the coming years. Cool. So yeah, I guess kind of going into some sort of more kind of general questions now, I guess. And as sort of a software engineer or a data engineer, how do you think this paper, like, what impact do you think it can have? What impact do you think your findings can have? Kind of going forward?
Yeah, so I think it will change fundamentally the structure of the query execution. So basically, it's just a one phase execution where you just join table in your execution phase. But now I feel maybe it's worthwhile to add another pre-filtering phase before this execution phase to reduce table first. Something like, so in a nowadays, there are already some pre-phase, but not pre-filtering. For example, you prune data blocks based on some coarse grained index like min-max. You also pre-filter something. So this can also be some kind of this pre-filtering. So maybe add between this coarse grained filtering and real execution. You plug this extra phase in the real system when you execute the query. And for real system, this will be a very large change in their internal engine. I can imagine, yeah, they have to put many people working on that if they want to support this. Yeah. And they also need to care about whether there are some suboptimal cases to fix that. And yeah, I would say it's a little bit non-trivial for commercial system to adopt that, but I think people will be more inclined to look into that and to see whether it will happen in the future.
Yeah, I mean, if the performance numbers are like, oh, this is definitely going to give us a massive speed up, it's worth the engineering effort, right? To sort of to get it into the system and deal with all of those sort of problems that might come from it from an engineering standpoint. But yeah, do you know if there's any sort of initial interest from any sort of commercial systems exploring this technique? You know, or is it still sort of too early for that? You think at the moment?
I currently don't know. Maybe I should talk with someone when I go for an internship this summer. I can get
Yeah,
to you some news on that.
yeah.
Yeah.
Cool. Yeah, awesome stuff. So yeah, I guess working on this project then, it seems like there's been some really interesting findings. I mean, I from kind of the outside looking in, but from the inside and working on the project, what is the
Mhm.
most sort of interesting insight or lesson that you kind of got from working on this project?
Yeah. There's one lesson which is not so closely to the relevant to the technical part, but there's a very interesting story. Yeah,
Yes, we like
actually,
interesting stories. Yes, go for it.
so this project started with a seminar where one student, which is also a co-author of this paper, who presented the Yannakakis algorithm. This is the origin of the project. And then my advisor thought had a very good feeling. I'm not sure how he had this feeling, but he just thought that we have opportunities to use that. Yeah, because he thought this is a very elegant, fancy algorithm, although it's invented way earlier ago, like 20 years ago. But my thought is, well, it was invented 20 years or even 30 years ago, but people haven't deployed it until today. I'm very concerned whether it's a worthwhile investigating that. And we have a very long and many times discussion on that. And finally, we figured out a way. So I think the lesson is that I shouldn't be too pessimistic on some old algorithm. Maybe we can somehow find a way to bridge the theory and the maybe industry or implementation into the practice using some other techniques, just like combine Yannakakis with Bloom filter. Yeah,
Yeah.
at that time I didn't realize that, so I'm very against on this project at the beginning, but finally I'm interested on that.
But yeah, you know you've been convinced, right? Yeah, so you've come around to
Yeah,
this method, yeah.
and yeah,
Uh,
totally convinced after some evaluation
yeah.
of that. Yeah.
But yeah, that's definitely a really interesting point about sort of not discounting something that's kind of like maybe more theoretical and older, but that's not sort of, it's like a hidden gem almost, right? You've kind of brushed
Yeah.
off the debt and then, yeah, give it, jazzed
Yeah.
it up for the 21st century and like, yeah, cool. Yeah, so I guess kind of related to this question, you touched on the origin story of the project there, that it was from a seminar and it sort of grew out of that.
Mm-hmm.
Was it kind of plain sailing all the way, or were there, I know you obviously had some kind of a bit of skepticism about sort of this idea in general, but were there sort of like any sort of bumps in the road or things you tried along the way that kind of failed, some dead ends, or was it just plain sailing?
I guess everything went smooth as long as we settled the detailed algorithm. For example, transfer from smallest to the largest, for example. Yeah, I guess there are some little things I got blocked. For example, for some cyclic curve at the beginning, I don't know how to do this because at that time I haven't settled down a specific order for example, from the smallest to largest. So say you have a triangle of the joining tables. if you do the clockwise or counterclockwise, there will be infinite transfers, right? You don't know where to stop because there always be a filter sent to somewhere. I need to filter that and use the reduce table to do another transfer. You always keep doing this. But yeah, yeah. And then we settle down the order, which is always from the smallest to the largest. And then there's no clockwise or counterclockwise cycle on this. So
Yeah.
there will always be a table which is smallest, whereas there will be no incoming filters for itself. Because this one is the smallest. Is only used to send out filters, but not receive a filter from other tables. And then
So
this gets stopped.
having these terminal sort of places has it stops the infinite loop, right? So yeah,
Yeah.
that's cool. So I guess now is probably maybe a good time also to sort of give some airtime to your other research as well. You kind of worked on as part of your PhD so far. So yeah, what
Yeah.
else have you kind of got in irons in the fire? What else are you working on?
Yeah, so before that, I'm mainly working on something like push down in the storage disaggregation architecture. So cloud databases. I previously working on cloud databases for our lab. So in the cloud, the storage and the computer are always disaggregated. So the network can be a bottleneck. So basically, people want to run some computation in the storage so that the size of the network will be smaller. So what I do is to, on top of this basic setup, and to do some further improvement. For example, if you have some cached data in your compute layer, you probably do not want to push down everything on your computation because you have some cached data. We can reuse that. So we just propose a hybrid solution to use the cache data on local processing as much as possible and do push down when there is a miss on the cache. And
Nice.
this is the one project. And another one, this is already finished on the first year. And another one is to enhancing its push down structure, which is we want to try to figure out whether there are more operators can be executed in storage. So before that, maybe people would just want to execute selection, which is filtering, and projection, and aggregation, which are very, very, how do you say, very the operators that are easily to get gains, but not complex to implement. People
I see.
people will
Right, yeah.
treat this as low hanging fruit. People
Yeah, the
implement
easy
it.
wins, right? Yeah, the easy wins.
Yeah,
Yeah.
people implement this in the field system, but we want try to figure out whether there are more opportunities to explore. Yeah, and we got some other ideas, but that's incurred too much details on that, I guess.
Cool. Yeah. So now you're kind of spending some time with the distributed execution. I imagine that's fun to debug when things go wrong. And there's but cool. So just a few more questions now.
Mhm.
And the first one or the penultimate one is about your creative process there. So you alluded to it earlier on and about the seminar process you kind of have in your group. But
Mhm.
how do you approach, like, kind of personally and as a group, idea generation? And then once that kind of is, doing your own sort of filtering to
Yeah.
choose which ones to work on.
Yeah, I would say myself as a researcher probably am not very good at creating very fancy ideas. I have to say, what I created just some of the small piece of ideas, and my advisor will say, "Well, it's a very good idea, but it's just a small piece of optimization on the existing tricks, so it may not worthwhile to wrap as a whole paper, for example." Yeah. So basically, what I worked on is just a discussion with my advisor and some other professors. Yeah, they gave me some hint that I think I'm not good at creating new things from scratch, but good at refining new things or refining semi finished ideas into a full-fledged ideas, for example. Yeah, the complete one. Yeah. So for
Yeah, but that
example,
makes sense, right? Yeah. Go ahead.
for
Continue.
example,
Sorry.
for this packet transfer one, we talk about family join. We talk about Yannakakis, and we think maybe we can do maybe optimize the semi join or optimize the round of the Yannakakis transfer. Because previously we would do forward and backward. Maybe we can optimize this rounds to get a better result to make it practical in the real system. But the I propose you just use two filters that it get combined. That's a very good example, I feel. And for some others, basically, they give me the hints and I pick what I feel most interesting or most reliable ones.
Yeah, that's nice.
So we
Yes,
have
you
many
can. Yeah.
ideas. Yeah.
Yeah, that's it. Yeah, but I guess using them as a sounding board and like leaning on their experience to sort of fine tune your ideas and then yeah, but I get where you're coming from on the kind of not like kind of reinventing something from or inventing something from scratch, but taking an existing invention and iterating on it and refining it and that I mean that's definitely a yeah, an important part of the creative process as well. I think is like standing on the shoulders of giants, right, and building
Yeah.
on this prior knowledge and then just tweaking it a little bit and coming up with something really cool and creative. So, yeah, I think that's awesome. So, yeah, last question now. So, what's the one thing you want the listener to take away from this chat today?
I see. Wow, that's a pretty good question, right? Yeah. So I think this project, which is Pack Transfer, can be a starting point of many other projects. And I really hope there will be more people in academia and industry who joining us to explore the very giant design space of these tricks. And let's see whether it will lead to fundamental change in the execution in the industry. And I hope it can happen. Just like worst case optimal dream. Some people say it will be the future in maybe a decade, for example.
Yeah.
And I want to make our techniques also the same case.
Yeah, well, I hope they are. Yeah, I mean, they look like it to me as well. So fingers crossed. But yeah, everyone's been told now. Yeah, so
Yeah.
great stuff. So yeah, I guess that's a wrap then, Yifei. Thank you so much for coming on the show. It's been a fascinating chat. I've learned a lot. It's been a fun wander through query processing. So yeah, thanks for coming on. And just to the listeners, if you want to support the podcast, please consider making a donation through Buy Me a Coffee. And another reminder that we have a survey out at the moment. So go and fill that in and have your say on how we can improve the podcast. And yeah, awesome stuff. And we'll see you all next time for some more awesome computer science research.